Hi, everyone. Welcome to today's webinar. I'm Shannon Butcher with PSERC. Thanks for joining us. Today we have Associate Professor Kate Davis from Texas A&M, and she's going to be presenting modeling, emulation, and testing for power grid cyber-physical security studies. If you have a question, please submit it to the Q&A box, and you're welcome to submit questions during the talk. They will be read at the end. Dr. Davis, please begin when you're ready.
Thank you. All right. Thank you to the organizers. And it's nice to be with everyone today. I'm excited to be able to join you all. So howdy, I'm Kate Davis from the Electrical and Computer Engineering Department at Texas A&M. So let's go ahead and jump in. I want to tell you about the goals of today. So today I want you all to be thinking about coordinated, scalable intrusion response for keeping the lights on. And what should that look like and how do we achieve it? So that's what our work is really about. And we'd love for anyone here to engage with us more on this project and this topic. So at the heart of this is the fact that electricity underlies the functionality of society, yet for the most part, most people take electricity for granted, at least until something goes wrong. So SCORE is about keeping the lights on. In other words, SCORE is really about how do we avoid lights off. So SCORE's research and development is being led through close partnership between academia and industry. Our team is a major highlight and we have long, extensive histories together. So Texas A&M is the lead with academic partners at Georgia Tech, Oregon State University, and George Washington University. On the industry side, we have Network Perception, who was recently acquired by Dragos, PSC, EPE, and TDI. And then we also have TEACS, who we work with on the workforce development side. And so SCORE is bringing together this strong academic industrial team to develop a scalable cyber-physical optimal response solution called SCORE as a key part of what a next generation energy management system should do. And SCORE also builds upon the transition of the team's prior successes, including Cypress, TDI's ConsoleWorks, CypSet, MPView, and NRI. And so today I'll be talking about grid resilience from a cyber-physical security perspective. So my goal is to get everyone to think about what a next generation energy management system would look like. I'll be talking about our cyber-physical energy management system concept as an enabler so that power systems can be modeled and analyzed as the cyber-physical systems that they are. And doing this right is the foundation for grid resilience. And I also want to get everyone thinking about the wealth of possibilities and open research questions that open up with these capabilities and leave plenty of time for future opportunities and other discussions. So first, what's the problem? Well, the problem is that large-scale power system operation and control is already complicated. Then the system only gets more complex and challenging when we really consider what all is really going on behind the scenes from a cyber perspective. So resilience of the grid is the motivation for this work, which is a key point. And the other key point is that resilience of the grid is inherently a cyber physical problem. It's not a cyber problem, it's not a physical problem, it's a combined cyber physical problem. And so providing grid resilience requires a cyber physical, trustworthy, and secure foundation. So to see this, power systems are large-scale cyber-physical systems whose electrical infrastructure is highly dependent upon its cyber infrastructure. And by cyber infrastructure, this includes all of the smart devices like relays and RTUs, all the way up to the monitoring and control networks that connect them and govern power system operations. And so devices in the field, all the way up to the monitoring and analysis and control systems, like an energy management system at a control center, govern power system operations and form an unseen backbone that underlies everything that we want and that we need the power system to do. And to see this, it's useful to look at the 2017 National Academy's report on grid resilience. This report has my favorite way of characterizing resilience, and it's a really great reference and provides good context for cyber physical resilience, even though now it's a couple years old. It talks about concerns about how the grid remains vulnerable to natural disasters, physical and cyber attacks, and other accidental failures. And this report conveys a need to develop comprehensive strategies amongst and between a range of stakeholders and on a range of timescales to prepare for, endure, and respond to events. And this is what we call the resilience life cycle, before, during, and after an event. And now this resilience life cycle perspective is crucial. It's necessary to engineer solutions at every stage to achieve the goal of cyber-physical resilient delivery systems. And it's especially pertinent for security. And so the cyber-physical security of this combined electrical and communications infrastructure is the core foundation. And on top of that, everything else that we want, that we need the system to do, can come from there. Because without this foundation, you can't have any of the parts above it, like the monitoring and detection, the coordinated control, and the grid reliability and resilience functions. These all require a cyber physical secure foundation. And so how do we do this? Well, part of the solution to how we do this and formulating strategies for how to respond is that we need to consider the grid as a cyber physical system, which it is, and avoid the tunnel vision of looking at parts of the system independently without regard for how the parts interact. And we also need to build capabilities of our resources for operating through failure. And that's what SCORE is all about, operating through failure across the life cycle of any of these events. And so in particular, all parts of this event life cycle matter, and they're all important. And they also all build on the previous parts, which is why modeling and test beds are so important. And so the solutions that we seek for cyber-physical optimal response solutions at all event stages are solutions of graceful degradation. And so for that, the question is, how do we selectively allow parts of the system to be removed from service while taking full advantage of the parts of the system that are still working? And so SCORE ultimately gets back to resilience enhancement. So SCORE is all about enhancing resilience by focusing on response. And to see this, we can consider this enhancement cycle that Hao Huang visualized well in his PhD work and classify techniques into 3 categories. So here is assessment, reinforcement, and response. And the SCORE project is in this response category. So before we get to response, we have assessment. And assessment means to better identify and predict the threats. And then this reinforcement phase is about the design that improves the system's inherent ability of absorbing disturbances. And the response, which is where SCORE fits in, is how the system can deploy the resources to proactively defend threats. And the infrastructure and operational resilience are interrelated. And having resilience in the infrastructure lays the foundation for operational resilience. So SCORE's sweet spot is really over here in the response part of operational resilience. And various techniques can be and have been applied in each of these categories. And for the response category, work is focused on cyber attack mitigation and remedial actions. And a lot of these also rely on the perception of the network structure and the assessment of the hazards. And so this is why it is shown as a cycle, because it's all related. And then it's important to note that infrastructure resilience lays the foundation for the operational resilience. So the need for a secure foundation and grid monitoring and control does not just matter for the grid. The US Department of Homeland Security named 16 critical infrastructure sectors where their assets, systems, and networks are so vital to the United States that their destruction or loss would devastate national security and welfare. And then a key point here is they all depend on power and energy, and most, if not all of these, are also cyber-physical systems. So therefore, it's very important to understand our systems from a cyber-physical systems perspective. And so what is a cyber-physical system? So this is how the National Science Foundation defines a cyber-physical system: as engineered systems that are built from and depend upon the seamless integration of computation and physical components. And so why is this so important? Well, a better understanding of power systems as cyber-physical systems informs us how to model, analyze, protect, and defend. And we can see from the critical infrastructure discussion that it's key for the welfare of the entire nation. I like to ask people about this, which is to consider some different threat categories. So you can categorize threats into some different categories, and then within each of those categories, there are different vectors and different specific ways that someone or something could enact events and cause consequences. So you can group them into natural, like extreme weather, and accidental and intentional. And so the question here is, which categories are cyber relevant? And of course, everyone immediately thinks of the intentional ones when you think of cyber incidents. But what is important here is that actually all of these are cyber relevant. And one that I like to talk about in particular as an example is this accidental category. And so a good example in this accidental category is data entry. So if you've ever looked at the power system model and all the data involved, it's quite immense. And there are many configurations and many model parameters and often many submodels. And so you can actually think about humans on the keyboard as a threat. It's so very easy to mistype a number and get a value that could be off by a factor of 10 and could go unnoticed. And this could affect the system, especially in a latent threat way, where everything may seem normal until there is some sort of perpetrating event. And then suddenly these little accidental errors and misconfigurations can have bad consequences as well. And so I like to put some context that actually all of these categories are cyber relevant. And we need to be even more concerned as cyber threats are evolving in sophistication and intruder knowledge. And this trend can be observed from the actual power disturbance reports, among many other places. You can just check the news and check recent reports. And there really is an increasing need for defense, especially against advanced cyber physical threats. And so the question is, how can we help the good guys get ahead and stay ahead? And so in developing the tools and techniques to address this, there are some key challenges and requirements that need specific attention. So the solutions we develop, they need to be scalable. Why do they need to be scalable? Power systems are large scale cyber physical systems. So we need solutions that are scalable both mathematically and practically. And solutions also need to be automatic. And that means the more that we can automate at least some of the things that are error prone and that don't need human involvement, the better. But this doesn't mean automating everything. And it doesn't mean taking out of the human out of the loop. It means automating solutions where we can and accounting for and working with and empowering the humans where we can as well. And the solutions also need to work for real world systems. And what this means in today's world and today's electric utility environment is that as much as possible, the solutions should work with the utilities today. We need to meet them where they are and meet them with the data sources and the software packages that they have and try to work with the real world systems. And so there's this beautiful balance that we get to strike between getting to design something that's entirely new from first principles and then figuring out how to take those first principles from some design that's entirely new and have that actually match up with and work with what's out there in the real world. And so that's what we get to do. And then the solution should also promote understanding and trust. So there are a lot of humans involved at different levels and in different roles, like power system operations, engineering, planning, security analysis. And we need solutions and approaches that promote more openness of the algorithms so that the humans can understand their capabilities and limitations and trust them, and to actually be able to fully utilize these technologies and advance the research in this area. And so it's about explainability and situational awareness. And then test beds are an important part of helping address these challenges. And so test beds are important for evaluating solutions and verifying that we meet the real world needs. And so to address this at Texas A&M, we've developed the Resilient Energy Systems Lab, or RESLab, which is a safe proving ground for designing and validating the cyber physical control systems of the future. So at Texas A&M, we've had several projects and team members that have been and are involved in related grid cyber physical security work. And this is the group of some of my students and research staff up here. Our work is working to bridge the gaps in cyber physical models, approaches, and tools to defend against advanced threats that can target physical power system impact. And the defense of these threats does require utilizing cyber and physical data and models together. And this is our focus. This is our sweet spot. And within my group's cyber physical security work, we've had the Cypress project, which focused on designing a next generation cyber physical energy management system that is inherently cyber physical and inherently considers security from the ground up. And the SCORE project that builds upon Cypress, focusing on intrusion response. And so now I want to talk a little more on the SCORE project, which builds upon Cypress, and how testbeds help us achieve this. So the research question we're answering is, what would resilient grid operation look like when the power system is given full consideration as the truly cyber physical system that it is? So our approach to answer this is to consider grid cyber physical security from a data flow perspective. So Cypress is all about finding out how to make the energy management data flow process inherently consider cyber state along with physical state. So to see this, you can think about what happens in a power system in terms of its monitoring, analysis, and control loop. And so that's why I refer to what we're doing as closing the loop with a unified model. So the first part of this approach in closing the loop with the unified model is modeling. So we have a cyber physical power system that needs to be modeled. And of course, it's the electrical side, but it's also the cyber side, which is just about everything else as well. Then at the control center side, a next generation energy management system will fuse cyber and physical network data, as well as generate models used in the analysis. And cyber physical state estimation, alerts from sensors on the cyber side are correlated with data from the physical side to infer what is going on in the system now. And the fused models and data allow us to do preventative cyber physical risk analysis, as well as inferences and predictions to enhance situational awareness based on the current state of the system. And then we can also see how well it matches up to the high risk cyber physical threats identified in the planning phase. And then those analyses provide recommendations for response and mitigation. And so we close the loop. So the cornerstone of our approach is to understand your system. So to understand risk to resilience, you need to know everything about your system. And this is probably one of the most important parts. The more you know about your system, the better. So modeling helps with this, and data helps with this, and I call it a map. So to find your way around something, it helps to have a map. And to defend a cyber physical system, it helps to have a map. So what does this map give us? This map gives us the union of the power system topology with the cyber network topology, and the intersection is a key part of the map. And then we create and leverage new modeling techniques and tools to provide system visibility into what the threats are, how far along a particular event or adversary might be, so that we can detect and defend it at an early stage. So understanding your system is a cyber physical security foundation. On top of that, everything else can come. Beyond understanding your system, part two, or the bread and butter of everything, is to fuse models and data to assess risk to resilience. And this is combining information from the cyber and control network side and the physical side to provide information to identify high-risk cyber attack-induced outages. And this provides cyber physical situational awareness and risk prioritization. And there are quite a few different approaches and techniques that we use to do this. The key idea is to have a cyber physical state space notion and cyber physical data fusion and algorithms that will be able to detect attacks early before they cause impact, and to provide the situational awareness needed to quickly recommend and take good countermeasures. So this is a key part of what a next generation cyber physical energy management system should do. And then the third part, the goal is to have a cyber physical response recommendation in the cyber physical energy management system that will build upon the previous blocks to answer the question of what next. And we've implemented some different proofs of concept along these directions where everything is cyber physical. And there's lots of research going on here currently. And so the good news is we've addressed a lot of the challenges so far. And now considering that context, this is the Cypress model and workflow, which we can talk about from left to right. So on the left are the data sources and major inputs into the model. So these alerts and data feed into and are managed by databases and tools. And these databases and tools feed into Cypress's mathematical model generator and manager. And so the top left portion is offline risk, which gives us a list of high impact and low cost access paths. And then there's the online phase from the models and data, which gives us an estimate of the compromised devices and paths and how close or far we are to what we predicted. And then both online and offline models go into risk management and mitigation. And here we do response recommendations and decision support, and we can do different visualizations specific to different user roles. And so this is how we envision the cyber physical energy management system working out and with SCORE and on also how we have been developing it. So here's an overview architecture of how the system looks in our test bed. So our test bed is a fusion of hardware, emulators, and simulators leveraged through the vSphere virtualization platform. So the cyber network is emulated using the Common Open Research Emulator, or CORE, and the physical grid is modeled in PowerWorld Simulator and dynamically operated using PowerWorld Dynamic Studio. And the protection components are modeled both with PowerWorld and with actual physical devices, such as the SEL RTAC, or real-time automation controller, which is connected to actual SEL 421 protective relays in our lab. And then the DMP3 protocol is used for monitoring and control. So CORE acts as a gateway for the physical and protection devices to communicate through it. So in CORE, we operate routers, firewalls, intrusion detection systems such as Snort, monitoring tools such as PacketBeat, and we use RESLab to put together experiments looking at different multi-stage threats to evaluate how well our different tools and mathematical models will work. RESLab is crucial for designing a next-generation cyber-physical energy management system, as our testbed gives us the safe proving ground for implementing our algorithms and our prototypes, and for implementing, evaluating, and defending against different threat scenarios. So for more information on our testbed and to check out our tutorials and sample cases, you can look on our website or reach out to me. And there's also a couple of the key papers for it on the bottom of the slide. Okay, so this is the old way and this is the new way. And so the people on the left side that are walking down this windy road, so that's the old way. And then then this is me over here on the right side, and that's the new way. And so this is actually what I used to tell my students. So back when I joined A&M and we were getting our lab started, and we were, kind of at the beginning of a lot of this, sometimes I would, tell my students what we needed to do, and they would say, "This is hard." And so then what I used to tell my students was it's about what is easy versus what is important. So for the people on the left, it's pretty easy to keep walking down that windy path, and maybe they'll get there eventually. But we see what we need to do here. Like all we have to do is knock this wall down, and the path will be straight. And I actually used to be a firefighter, so that's me with the axe because I know what to do with an axe. And so the good news is I think the wall has been knocked down more or less. There are big holes in it now, at least that we can climb through. So I think that the situation now is a lot better than it was 10 or 7 years ago. So and I think it's good news. There's the way that the energy sector is taking power system cybersecurity really seriously has been really good. And there've been a lot of improvements. And so this is the new way. So this is the cyber physical energy management system, or CYPRESS. So the CYPRESS analysis must be evidence-based, scalable, proactive, and business aware. And the solution is both physics-based and data-driven. And it's also a life cycle solution that can be used to assess and manage risks related to deployability and maintainability of assets. And a research focus that's continuing to go on is on cyber physical risk analysis that is practical and evidence-based and proactive. And proactive means that we do key modeling and risk assessment ahead of time and implement changes ahead of time. And even saying ahead of time has different relevant timescales here. So there's the planning and the architectural timescales up until early in an incident kill chain, where there is still time to prevent more catastrophic cascading events and losses. And this is called left of boom. And so there is also a need to understand how to incentivize this successfully for stakeholders within a regulatory environment. And questions arise of how a utility organization should deal with security event management holistically, not just technically, but from a policy and communications and from a liability and legal perspective as well. And so that's also something we see as really important. And then so transitioning from Cypress to test beds, it's about how do we take the techniques we develop and help utilities deploy them? And the answer is the test bed. So the test bed and test beds are a key part of the solution. And then the question is, what do we want from it? What do we want from the test beds? And some would say digital twin, but basically high fidelity models. And the answer to that is all of the defense solutions. And it's getting there, and I really think it's good news that we've come a long way. And now I would say that with work, including this work and work that others have been doing in the cyber physical power system research community, now is it's more important than ever. This is the right time, and we can finally gain more headway on the remaining challenges because now we can stand on the shoulders of strong foundations that have been built over the past decade. And so it's really an exciting time. So we're finally here, we're finally at the top of the mountain, looking down to see what's on the other side and ready to choose what our new path to jump on should be. And so how do we do that? So it means we need to consider the cyber and physical together. And so the question we need to be asking is, how do we close the loop with the cyber physical model? And it gets back to the resilience life cycle. It's taking and building the cyber physical model from monitoring to analysis to control. So it starts with modeling and then verifying. So to verify, you need a model and you need a simulation or an emulation, or you need what some call a digital twin. You need a test bed. And so to do the more advanced analysis and control, one needs a solid foundation first, and that includes the model and the situational awareness of the system that it models. And so we call this CYPRESS, which stands for Cyber Physical Resilient Energy Systems, because that's the ultimate goal. And so at each one of these stages of the cycle, the lab is crucial. So the lab or the test bed is what gives you a safe proving ground. And the safe proving ground is necessary to do research in each one of these stages properly. And so in particular, test beds help us because they help us have an agile research and development cycle. And what do I mean by agile? So what this means is that for the problem at hand, whatever the particular security threat is that we're looking at, or whatever our particular threat model, then we can start with conceptual designs that guide the team to determine how to model the scenario and what data we need, including how to best utilize and expand our testbed resources. And we update it as we go and evaluate it as in this cycle. And so for us, this is our Resilient Energy Systems Lab or RESLab testbed. With the testbed, we can design and validate solutions at all stages of the event lifecycle against cyber and other high impact, low frequency threats. And so this is our Resilient Energy Systems Lab, RESLab testbed. And this is built upon the vSphere virtualization environment, which allows for the creation and management of a large number of VMs. In RESLab, connections between emulated and physical components are made to scale the network depending on the use case. And now an example here, which my student Lean shows in this video that's linked on the right. So this is a multi-stage, multi-area intrusion that we've modeled in our test bed to try to better understand how these threats might look in real life and how to better defend it at each stage. And so the idea with this one is that the intrusion would start in the utilities and moves all the way up to affect the balancing authorities. And the protocols involved in this use case involve multiple major protocols such as DMP3, SQL, and ICCP. And a walkthrough of the use case is detailed in this Smart Grid Com 2023 paper that's shown in the slide. And so for more details, you can check that out. And so the models and scenarios and data sets from scenarios like this one and in realistic cyber-physical test beds like ours are something that can be and are really useful in the research community to help with facilitating research reproducibility and also to help with rigorously validating the assumptions that exist in certain aspects of this complicated system under study. And even its implementation of different features like firewalls and protocols, which may often be overlooked. And it can be very simple or very easy to simplify those details away. And so then we really can see that the devil's in the details when we look at developing any of these scenarios. Since we're trying to mimic the scenario with a great deal of accuracy and capture that in models and simulation and emulation, then there is also a challenge with the test bed, as its models have to be very good and it's a lot of work to develop. And so there's this balance that we have to strike. And I hope that could be something we may talk about more during the Q&A, because it's kind of an interesting topic. So hence this new scenario for ICCP was led by the Texas A&M team in close collaboration with some of our other project partners, and in particular PNNL and Mark Rice at PNNL. And so based on the MITRE ATT&CK framework, we developed this scenario consisting of multiple stages. And so there's some references on here about the MITRE ATT&CK framework. So we were mapping our stages to the MITRE ATT&CK framework. And so on this figure, the gray circles indicate the steps that were implemented in this example, and then the black circles are assumed or not implemented. And then all the circles are the steps in the MITRE framework. And so the multi-stage use case was developed and presented at Smart Grid Com in the RESLab testbed, originally for Cypress, and we're extending it in SCORE based on the MITRE ATT&CK framework. So we have 4 stages of intrusion. We have reconnaissance and initial access, persistence and escalation, lateral movement and physical impact. So in the reconnaissance and initial access, the adversary is trying to gather information to plan future operations and trying to get into the network. Persistence, the adversary is trying to maintain its foothold. And then with privilege escalation, the adversary is trying to gain a higher level of permissions. And lateral movement is the adversary is trying to move through the environment. And then impact is the thing that we really worry about from the power system resilience perspective is this impact stage. And that's where the adversary is trying to create some consequences on the system, trying to manipulate, interrupt, or destroy your systems and data. And so as we develop new use cases, we map them to the MITRE ATT&CK framework. And likewise, we also map the detection, defense, and response mitigation steps. And so in this case, in step 1, this is the reconnaissance step, and the intruder scans and finds an open port to the corporate network. And then in step 2, the intruder reaches the corporate network, and the corporate employee machines can access a database and web server in the public DMZ. So DMZ is a demilitarized zone. And then the intruder manipulates data in the database in the public DMZ using SQL injection. And this could be, the manipulated data could be status of breakers or the flow on a transmission line or generator info. And then steps 4 and 5 are the data manipulation. So here the ICCP node in the control center gets manipulated data from the database, and the ICCP node pushes the manipulated data to the balancing authority. And then the balancing authority sends the command to the ICCP node in the utility. So maybe that's going to be to decrease generation because of the manipulated data it receives. And then the ICCP node inside the utility tells the SCADA master to change the generation and to what value, and the command is sent. And so one of the major success stories is putting all of this together for this case and others like it and implementing it in the lab and the response development in the lab environment. And so the intruder's path, you can kind of trace through the figure here on the slide. And so ultimately, if this threat is not stopped, then it could lead to some physical impact. And so the first layer of defense developed against this multi-stage use case is the use of data fusion to combine both the cyber and the physical data collected and input it into an autoencoder to detect the intrusion. So we use an autoencoder to compress and compare the data. And what was interesting is that in this use case, which we go into have the details on the data analysis in this paper, what we found is that the cyber data alone is enough to detect and mitigate the attack early, and this is a good thing. And so this is also, then we also have to assume that the attack does get detected then. So it's important to highlight that here we're assuming that the intruder's attempt to spoof the network is detected early, since we've shown that can be done. And so that means that since the intrusion is able to be detected and mitigated early, then there won't be any forged generation values that will be sent, and no forged data will make its way to an outstation and cause physical impact. And so that's a good thing. And in developing these detailed scenarios and creating them in our test bed to analyze defenses, the goal is to help us develop scalable, security-oriented cyber-physical response solutions that would sit on top of a next-generation EMS and SCADA to determine how to respond in a timely and semi-automated manner. And so there's an 8-minute demo video here, which you can check out on this scenario, and there's a QR code to it. And then we think about all of the what ifs. And so then what if the threat gets through undetected and those early mitigations fail? So previously we saw that we can see some cyber indications of impending physical impact, but the cyber side data alone is more than enough to detect the attack early and respond. And this makes sense, and that's also good news. So maybe just like one simple takeaway is to, if you're on the power system, go talk to and thank your cyber colleagues, because they're doing some good work on the cyber side that can prevent a lot of bad multi-stage threats from getting worse. But so now, what if we assume that it does not get detected and mitigated early, and then there is physical impact? And so with the physical impact part, we model the dynamic response on both the physical and cyber sides, and then we want to launch SCORE. And so in this use case, we're assuming that an early defense mechanism does not succeed, and the intruder is able to continue moving laterally in the network undetected. And so the plots below show the values before and after the new DMP3 commands with these malicious values are sent. The second layer of defense against this threat is the simple network reconfiguration algorithm. So a communication network is constructed for this use case and modeled in our test bed. An important step to implementing this network reconfiguration is to focus on the physical impact first. So following the results of the earlier parts of the scenario mentioned. So how the physical system actually responds is a really important part of how we need to proactively respond on both the cyber and the physical sides. So to implement network reconfiguration, we need to have the system first reach a stable point. And we continue to work a lot on the cyber physical scalable intrusion response. We developed an algorithm on cyber physical control action selection using rerouting and physical dispatch with the paper that will be presented at the PES general meeting. So the algorithm optimizes the operation of both the cyber and physical components and power systems in response to a cyber attack. And we're currently working on a decentralized algorithm, which will make it scalable for larger scale systems. And the multi-stage intrusion and defense scenario journal paper is shown on the slide. And we also have a recent journal paper on comparing multi-agent frameworks, which is shown on the slide. And this is informing our next steps that we're working on now in SCORE on multi-agent RL methods to upgrade our earlier algorithm, where we have another journal paper for the earlier algorithm, which is still in review. Okay, so now getting back to test beds and verification and validation and how all of this relates to response development. So in understanding how to respond, Cypress plus the RESLab testbed allows for interactive defense. So the testbed lets us do multi-user interactive operation of the power system, and it lets us explore how different adversaries and defenders can act in a real-time manner and has interaction in real time with Power World and is intended to act as an environment for adversary and defender agents. And we've used this in a number of hands-on tutorials and demonstrations, and it's a neat capability. On practical cyber-physical risk analysis future work, we're also digging deeper into a process for evaluation and scenario development assistance and guidance of cybersecurity technologies of investments for the grid based on substation and control network technology improvements. And so here we can consider details like how the upgrades in substations are often done as multi-phase solutions with multiple parties involved, and how to deal with issues that could affect reliability and resilience in latent ways like maintenance contracts and supply chain challenges. So the supply chain can be hard to keep up with, particularly if a vendor may not exist for long. And so we seek in our testbed to capture the intrusion processes and behaviors while including the security technologies representative of a realistic defender. And then we use this to infer credible threats considering different operational objectives. So with testbeds and VMV, how do we rigorously perform and quantitatively compare grid cyber-physical security experiments? So we want to build upon our recent prior work in this area with our Sandia National Labs colleagues on reproducibility. And that is, how do we claim that an experiment has been successfully replicated or reproduced? And this is a challenge, especially in the cybersecurity field, and it has not been given the proper amount of attention that it deserves. So even if one wishes to replicate the exact same experiment, there are challenges. So inherent variability in the cyber network results can be due to system timing, resources, different operating systems, kernels, and other factors. And we need a way to better understand and quantify these differences to understand how technologies will actually behave in reality versus how different testing environments may actually impact or bias or skew the results. So the idea is to do this for different architectures and technologies and vendors in the cyber physical power system. And the idea is to develop a rigorous comparison pipeline or process to study and compare the substation and control center technologies. And so some of the interesting research questions here are the metrics to determine effects of different architectural and technology settings on the results, and then the generalizability of the metrics. And so to show intrusion and detection in the loop, we implement some use cases. And so this is a figure showing what one of those use cases looks like. So this is an ARP spoofing where the adversary sends false ARP messages over a local area network to effectively become a man in the middle. So the adversary can receive packets from the master as an impersonator for the outstation and modify the commands and forward it to the outstation. So in this way, the intruder can sniff traffic, modify measurements, modify commands, cause network congestion. And our test bed allows us to analyze all the interesting timing details, which feeds into our data fusion and response algorithms. And we go into more detail on the detection and mitigations for this scenario in the paper and the demo, which is cited on the slide there. And here is an optional do-it-yourself lab on the experiment that I showed on the previous slide. And so if you go to this link here, you will also have a demo tutorial video that will walk you through it. And our paper talks about how to put together several of these ideas and make them actionable for power grid, cyber physical data fusion, for cyber physical state estimation. And so to map it all, so we've got the risk and planning phase where we identify high risk scenarios. And then there's an example of the ARP spoofing attack, what that might look like. And our test bed allows us to collect all of the data and look at the timing details. And we can also implement off the shelf things like Snort IDS, where we can implement our own detectors to generate alerts and forward those either to our central application or decentralized application in real time. And then in the response, so we're reconfiguring the cyber network in which the routers can change their routes on the fly. And so we can do things in this response block as well. And then mapping with the models. So the goal is to have a cyber physical response recommendation engine that builds on the previous blocks to answer the question of what next, where everything is cyber physical, and then bringing it all together with Cypress, Score, and our RESLab testbed. We can help provide validation, detection capabilities, and early warning indicators, and mitigation information, and how to convey that to people and tools to help them do their jobs better. And that is cyber physical situational awareness and visualization to help different stakeholders. And so in RESLab, we want to further compare and assess different field devices. And so one question is, how do we take the techniques we develop and help utilities deploy them? How do we make our lab more accessible to them? And so to help bridge this gap, we created a tool called Open Conduit, which is an MPView to core data pipeline. And so this takes the network data and converts it into a form that can be read by our test bed, so we can construct a very realistic model in our test bed from the real world configurations. So this is what it looks like. So Open Conduit converts the network configuration files and creates a real-time environment for our test bed that includes routes, firewall rules, and taps for hardware in the loop. And so there's a lot of industry applications for this, and you could also call it a digital twin, or could be. And then this technology and this approach can also be used to take something that is not a real network, but would be a synthetic network, and create it as a honeypot that you can plug into a real network and instrument as well. And so I list all three of these things in the title because there's some big similarities and they're related. And actually, there was a honeypot use case that was a big focus in 2023 for us. And so the Open Conduit program, compared to a manually constructed honeypot network, is a fully automated and designed to work with any network that is input into MPView. And so there was a new version of this that was created in 2023. The first version was created in 2022. And so we have a demonstration of this that's recorded in the video. And I think there's a lot of more interesting things that can be done with this. And so it's like thinking about there's a potential use case on cyber deception and the use of digital twins here. And so that's so what we're working on now is scaling up. So we've been integrating Score with the Cypress EMS and working on the response and reconfiguration studies in our RESLab testbed, scaled to large cases. And we're also working on developing a trusted computing base for Score and for the Cypress EMS code. And we have a new tool we've been working on called Destiny to replace the old Cypress EMS backend. And we have a little video that shows the Destiny tool, which is extremely lightweight and scalable. And we can run it on the 10,000 bus cyber physical case, which we generated, which is 4 times larger than the 2,000 bus. And it's a very generalizable code. And so there's actually a lot of exciting developments going on now with Destiny. And I think for my next time I do a PSERC webinar, I'll probably do a deep dive on this slide. And so then just to kind of wrap up the key points here. So this is all about cyber physical verification and validation, and why test beds and cyber physical models are so important. And so they can significantly help the industry do repeatable research in our area. And the idea is to use models of increasing sophistication and detail to develop power system cyber physical defense tools. And it's an iterative process. So you start small and build up, and you simulate and emulate and collect feedback from stakeholders. And so then you repeat that. And so finally, a key takeaway point is that a key part of achieving long-term sustainable success on this problem is partnerships within and for the energy sector. And so the tagline on that is grid cyber physical resilience involves everyone. And so just the last uh, thing I want to mention here is it's the last night I had the HCAN officers over for dinner. So HCAN is the Electrical and Computer Engineering Honor Society, in case you haven't are familiar with it. And I'm their faculty advisor. And I thought these are our next generation of technical thought leaders. And the good news is that the next generation totally gets it, and they're totally capable, and they're totally willing to step up to the bat. And so that means it's up to us to train them, to empower them, and to pass along the torch and to give them this agency to help solve the problem. And that's important because we need them and it takes everyone. And so I have a lot of happiness and hope for the future because of these students and all my students and others like them. And on that, you can also see in this picture here that I'm about 7 months pregnant, due in July. And so this is also my way of saying I won't be able to be with you guys in person at the PS General Meeting in Austin or the PSERC meeting this summer, though those are going to be great events as this little guy will be making an appearance. And with that, that will conclude my talk, and we'll take a couple of questions if there are any questions. Thank you.
Dr. Davis, it looks like we have 2 questions so far. Oh, 3 actually, down in the Q&A box at the bottom of Zoom.
Okay, let me see if I can find that. Oh, okay, I see. Cool. Yes. Okay, it says, how would you see digital twins fitting into the cyber physical modeling framework? In your opinion, should we be putting test beds and digital twins in different siloed buckets, or do we need to adopt a new way of bringing these two under the same umbrella of a unified framework? I think maybe it kind of depends on what the purpose is of the test bed or the digital twin. I think in some ways I can see them being the same, but then I can also see really specific digital twins or test beds being developed in a very, very specific way for a very specific purpose. And so maybe that just means you may need more than just one, I guess. So yeah, maybe you would, I think they could be grouped together, or you could have different ones. Okay, let's see. The next one says, thank you for sharing your experience on this topic. How feasible do you believe it is to develop a high-fidelity digital twin capable of reliably training reinforcement learning models for detecting cyber threats? I think it's completely feasible. I think this is where I think it's, let's see, given the inherent complexities of operational power grids and distribution utilities, including the sheer volume of data from grid infrastructure, coupled with dynamic environmental variables like weather patterns and equipment aging. I think it's feasible. But yeah, like you kind of the rest of your question points out, I don't think it's not trivial, but I do think it's feasible. I think now is the right time to be trying to do that. And then the last one says, these tools can be very useful for the industry and academia. Will some of these tools be open source? So yes, that is our intent, is always to make our tools open source. The challenge, which I've started to identify, so before I came to A&M, I used to work for PowerWorld, which is I developed commercial software, but it's a little different developing software, I guess, at a university. It's like we want to make them all open source, but the challenge seems to be that like the funding for projects ends, and then we have to like figure out like kind of a good systematic way to do that at something other than just a research grade scale, so it'll actually be useful. So I've been thinking about different ways to do that, and happy to get ideas. Thank you.
Okay, Dr. Davis, I think that concludes our Q&A. If anyone submits an additional question, we will provide that to Dr. Davis after the webinar today. She's welcome to answer separately via email. We want to thank everyone for attending and thank Professor Davis for giving us this presentation. As you can see, I have launched a tutorial poll. We would appreciate it if you would answer this quick question. It helps us improve our webinars. You'll find slides and a recording of this webinar on the PSERC website. And this was our last webinar before summer. We do have summer tutorials coming up, June 4th, followed by June 18th and July 9th. We hope to see you there.